In the last video, we introduced the concept of work. Energy is closely related to work. Energy is quite easy to measure, but it's less easy to define. Therefore, in this video, we will first explore different types of energy and how to calculate them, and then discuss what energy means. One type of energy is associated with motion. Here, the red block is moving, and so we naturally think of it as having some sort of mobile energy. The blue block is at rest, so it lacks that mobile energy. The correct name for mobile energy is kinetic energy. Objects in motion have kinetic energy, while objects at rest do not. The kinetic energy of an object is given by this equation. Kinetic energy equals 1/2 the mass of the object times its velocity squared, half mv squared. Like work, it is measured in joules. That v squared is significant. It implies that kinetic energy depends more on velocity than it does on mass. In fact, whenever the velocity of an object doubles, its kinetic energy is quadrupled. We'll see this effect play out in this example. Calculate the kinetic energy of a 2 kilogram object if its speed is A, 3 meters per second, and B, 6 meters per second. For part A of this question, we were told that a 2 kilogram object was moving with a velocity, or more correctly, a speed of 3 meters per second. And we were asked to find out what the kinetic energy of this object is. Not very hard to do. Kinetic energy is 1/2 times mass times the velocity of the object squared. So, 1/2 times the mass, which is 2, times the velocity, which is 3. Now, strictly speaking, velocity is supposed to have a direction over here. But since it's getting squared, the squared is basically taking the dot product of velocity with itself, so the direction is going to go away. And we're going to end up with 1/2 times 2 times 9, which works out to 1/2 of 2 is 1, times 9 is 9 joules. So this is the quantity of energy contained in this 2 kilogram object that is moving at 3 meters per second, 9 joules of energy. Again, remember, energy is a scalar. It does not have a direction to it. Part B of this question was saying, what if you had the same 2 kilogram object, but this time instead of moving at 3 meters a second, it was moving at 6 meters per second? In this case, the kinetic energy would be 1/2 mv squared, obviously, that's the formula for kinetic energy, which works out to 1/2 times mass, 2, times velocity, 6, squared, which is 1/2 of 2 times 36. 1/2 times 2 is 1, 1 times 36 is 36 joules. So what we observe over here is that if we have an object, let's say that it's starting at the origin, it's moving in the positive x direction, we can easily find out what its kinetic energy is going to be by using the formula for kinetic energy. And we also see that mass is less important for kinetic energy than velocity is. A change in velocity has a bigger impact because the velocity gets squared. So if the velocity doubles from 3 to 6, the kinetic energy is going to quadruple from 9 to 36. Again, kinetic energy, like work, is a scalar. That's because when you square velocity, you're taking the dot product of the velocity vector with itself, and dot products always yield a scalar. Notice that kinetic energy can never be negative. That's because you're multiplying mass, which is positive, by velocity squared, which must also be positive. Thus, there's no such thing as negative kinetic energy. However, an object can have zero kinetic energy if it isn't moving. In that case, the velocity is zero, so naturally the kinetic energy is also zero. Now, let's look at the second type of energy. In this animation, a ball is held at a height, but it can only remain at that height because someone off-screen is holding it. If they let go, the ball would fall. Any object in an unstable position will start moving when it is let go. We say such an object has potential energy. Potential energy is the energy an object has due to being in an unstable position. Like kinetic energy, it is a scalar, measured in joules. There are several subcategories of potential energy. We will see two examples. To return to our ball, the reason it is in an unstable position is that gravity would pull it down to Earth were it not held in place. Gravity is the reason the ball is in an unstable position where it starts. And so we say the ball has gravitational potential energy, energy due to an unstable elevation. The equation for gravitational potential energy is as follows. Gravitational potential energy equals the mass of the object times acceleration due to gravity times the height of the object, mgh. On Earth, g is the familiar 9.81 meters per second squared, but we always treat it as positive in this calculation. Consider this example. You are 1.5 meters tall. You hold a 3 kilogram ball 1 meter above the ground. What is the gravitational potential energy of the ball? Let's start out by drawing this situation. Here's a person who is holding a 3 kilogram object. We want to find out what the potential energy of this object is. Before we start, of course, we have to set our origin and axes. Now, solving for the potential energy due to gravity is pretty straightforward. You just take mass multiplied by gravity and multiply that by height. We were told that the ball was 1 meter off the ground. So that works out to the mass, 3 kilograms, times g, 9.81, times the height, 1 meter, which works out to 29.43 joules. Easy enough to do. So now we've worked out that this ball has 29.43 joules of gravitational potential energy. But suppose that I look at this slightly differently. I'm going to draw exactly the same situation. Here's a person holding exactly the same ball, exactly the same height off the ground, but I'm going to do something slightly different. I'm going to draw the origin up here at their head, and I'm going to set upwards as positive. Remember how I always said in kinematics that the position of the origin doesn't really matter. It just says what your perspective on a question is. You are free to choose wherever you want it to be as long as it makes the question easy to solve. Well, in this case, let's say that I set it at the person's head. The distance from the origin to the ball is now only 0.5 meters. Let's say that this person is 1.5 meters tall. And this ball is now below our origin. So what is the potential energy? We still calculate it the same way. The mass times gravity times the height. But the height is now 0.5 below the origin, which is negative 0.5. How much does all of that actually come to? 3 times 9.81 times negative 0.5 gives us negative 14.715. Now, this looks like a problem, doesn't it? We have now gotten a second value of potential energy that has no relation to what we got the first time. How is this possible? The answer is the value of potential energy depends on where you set your axis. And what we usually find is that when it comes to gravitational potential energy, the first thing that's surprising is you're allowed to have a negative value. You were not allowed to have a negative value of kinetic energy, but you are absolutely allowed to have negative values of potential energy, specifically gravitational potential energy. So that can happen quite easily depending on where you set your axes. The other thing is, how do we reconcile the fact that we got two different values here? The answer is that the quantity of gravitational potential energy usually is not the most important thing in a question. It's rather the change in the gravitational potential energy which does matter. It's sort of like how when we were doing kinematics, the position of the object relative to the origin was not really all that important. It's the displacement of the object that matters. In the same way, the absolute amount of potential energy is usually not what matters in one of these questions. It's the change in the amount of gravitational potential energy which does matter, and that will always be consistent regardless of where you set your axes. To summarize, gravitational potential energy includes some subtleties that are not present in kinetic energy. Unlike kinetic energy, gravitational potential energy can be negative, and its value depends on the location of the origin. There are other types of potential energy besides gravitational potential energy. That's because there are other ways that things can be unstable besides being elevated. Here is a compressed spring. When it is released, it will press the platform outwards. A compressed spring is in an unstable position, and it will expand to its natural length. A compressed spring has spring potential energy, and the amount of potential energy is calculated as 1/2 times the spring constant times the compression of the spring squared, half k delta x squared. Let's apply this. You have a spring of spring constant 500 newtons per meter. Calculate its potential energy if it is A, stretched by 0.2 meters, and B, compressed by 0.2 meters. In part A of this question, we have a spring which has been elongated. And at the end of it is an object which is 2 kilograms in mass. Actually, we were never told what the mass of the object is. Doesn't matter for our purposes. I'm going to set my origin to be at the natural length of the spring. Let's say the natural length of the spring was over here. I'm going to set my rightwards direction as being positive. So the elongation of the spring over here was 0.2 meters. We want to calculate what is the potential energy in this spring. Easy enough. The potential energy of a spring is given as 1/2 times the spring constant times the elongation or the deviation from the natural length of the spring squared. So we were told that the spring constant was 500 newtons per meter. So potential energy of the spring is half times 500 times delta x is 0.2, and that gets squared. So half times 500 times 0.2 squared is 10. So that is the potential energy that is in this system with an elongated spring. The spring being in the unstable position of elongation as opposed to its natural length. Just like what we saw with velocity, the displacement of this object is a vector, but when we square it, it becomes a scalar. So this entire expression just boils down to a scalar of 10 joules. Now, what about for part B of this question? In part B, we were told that the spring was not elongated by 0.2 meters, but rather compressed by 0.2 meters. I'm going to keep my origin at the natural length of the spring. I'm going to set rightwards as positive, and this time I'm going to have this displacement be 0.2, but since it's in the negative direction, I should correctly say that delta x is negative 0.2. K is still the same as before. We want to find out what the potential energy of this spring is going to be. It's going to be 1/2 times K times delta x squared, which is 1/2 times K is the same 500 as before, times delta x, which is now negative 0.2 squared. You can probably see where this is going. The negative is going to go away when you square it, which means that this calculation will be exactly the same as this one. So it's going to work out to the same 10 joules. Same amount of energy, regardless of whether you elongated the spring or you compressed the spring. And that occurs because the sign gets removed, basically, when you square the deviation from the natural length of the spring. While a stretch has the opposite sign of delta x than a compression, the displacement term gets squared anyway, so the result cannot be negative. Indeed, unlike gravitational potential energy, spring potential energy cannot be negative. At this point, we still haven't defined energy. Let's take another look at each of our animations. The red block has kinetic energy. It collides with the blue block and then starts pushing. In other words, it applies a force on the blue block as it pushes it through a distance. It does work on the blue block. The elevated ball has gravitational potential energy. It falls on the seesaw and pushes the block through a distance. Thus, it also causes the block to experience work. The compressed spring has spring potential energy. When it is released, it applies a force to the platform and pushes it through a distance. It does work on the platform. In all these cases, an object that had one or another form of energy caused another object to experience work. Let's use this as a definition of energy. Energy is a measure of how much work an object can do. The total amount of energy an object has comes from two sources: kinetic energy and potential energy. Now, remember how in kinematics we used to take two photos of the system? Let's apply that to the first animation. Let's take photo 1 here. The red block is moving, and so it clearly has energy, specifically kinetic energy. The blue block is at rest, so it has no energy. As the red block collides and does work on the blue block, it visibly slows down. It loses energy. Vice versa, the blue block speeds up from rest, gaining energy. if we take photo 2 here, we would see that the red block has less energy than it did at photo 1. Meanwhile, the blue block has more energy after the work was performed on it. Let's generalize this observation. The total energy of each object in photo 1 is different from the total energy of each object in photo 2. When an object has work done on it, it gains energy. When it does work, it loses energy. This equation is known as the law of conservation of energy. It says something very profound. It says the total energy of an object cannot change unless work occurs. A more familiar way of phrasing that is energy cannot be created or destroyed. That's what it means when we say energy is a conserved quantity. Conservation of energy is a centerpiece of physics. In the next 2 videos, we'll see how to apply it to different puzzles.